So hello, is my voice audible right now?
Yes, sir.
Okay. So welcome to the course of signal processing for millimeter wave communication for 5G and beyond. And this is the assignment for week 7. So let us start from the question number 1. So the first question is, for a millimeter wave measure system with single reflector, every path gain is considered to be of. The option A is nearly same amplitude with defined phase difference. Option B is same phase difference with considerable different amplitude gain. Option C is different amplitude and different phase difference. And option D is similar amplitude and phase difference. So let me solve the problem here. So the first question here. The question is, I have a meso system here. So what does meso system means? This is multiple input and single output. So for a meso system, the structure will be like this. This is first antenna, this second antenna, third antenna, and there is one receiver antenna here. So if we do some sort of transmission from these antennas, so this goes, sorry, first beam is going like this, second beam is going like this, and the third beam is also going like this for this single antenna. So see, all the beams, they reach the receiver antenna parallelly. If it is the RX receiver side, they all reach the RX side parallelly. So if it is the case, we can consider that the path gain is almost constant. However, there is a distance between each of the antennas. So this distance will be converted into the phase difference. Why? Because if it is the first path, like it is nearest to the receiver antenna and it has a small difference between D. So suppose it reaches at T1 and it reaches at T2. So they will cross the same path for a receiver which is situated for a long distance. But the thing is only the small distance d, this will generate the phase difference here. So the path gain will remain for all the paths, that is alpha I, this will remain constant. However, there will be d, that is the distance between the antennas. This distance will generate different phi. terms. This includes theta and phi component also. So the correct option will be, let us check the options. Nearly same amplitude with different phase difference. This is the correct answer. Same phase difference cannot happen because every receiver antenna has a difference in between them at D, and that will create some sort of phase difference. And so option B is just completely counterpart of the option A. So option B is surely wrong, and the different amplitude cannot happen. So option C is also wrong. And similar amplitude can happen, but phase difference cannot be similar. So the correct option is option A. So correct option is option A. For question number 1. So is it clear for everybody? Hello? Is it audible?
Yes, sir.
Okay. So let us come to the question number 2. So question number 2 is, for a single reflector millimeter wave system, there are two transmitter side antenna and two receiver side antenna. So the question is, what is the number of unknown variable for the channel estimation R? So anybody can answer this question? Any approach from your side? Like it is a 2 cross 2 antenna system, but the configuration is like for millimeter wave, and there is only a single reflector there. So like you can think there is only one reflector and that is getting transmitted that has a path gain alpha I. So how many there will be? Okay, let me solve the question. So question number 2, it says it has a 2 cross 2 antenna system. If it is a 2 cross 2 antenna system, so two transmitter side antenna, this is the first one, this second one, first receiver antenna, second receiver antenna. So what is the channel matrix equation for millimeter wave channel? That is HL is equal to alpha I is equal to 1 to n, and this is AI R. This is the receiver side array manifold sort of thing, and this is the transmitter side array manifold type of thing, and this is the transpose. Because this is channel matrix, this form will come a matrix. So this is the matrix. So what is n here? So first, what is n here? N is equal to 1 because there is single reflector. And what is uh, this AI? AI is a nr cross 1 vector. So there are nr is equal to what? Nr is equal to 2, and it is also 1 cross nt. It is also nt cross 1. This is also a vector that is in the transmitter side. So nt is equal to also 2. So it has two part, it has two part. So total is nr is equal to 2, nt is equal to 2. So total number of unknowns are 5. That I have to estimate. And so the right option is, for second question, is option B. And another point here, because this is the channel matrix. Can you guess what is the dimension of this channel matrix for a 2 cross MR cross MT antenna system? Like if there are MR number of, so this, the dimension of the channel matrix will be MR cross MT here, because sorry, for this case, as we have discussed, dimension of the channel matrix is NR cross NT. Because of this configuration, it has NR number of term and it has NT number of term. So NR cross the actual channel matrix will become NR cross 1 into 1 cross NT. So dimension of the channel matrix here is NR cross NT. So we can think there are NR cross NT number of variables, but that is not for millimeter wave communication. But if it was sub 6 GHz, there could be NR cross NT number of variables. That is not because we do sort of beamforming here. Directly. There is no, this term there is not present here. So let us go to the third question. For a millimeter wave communication beamforming, which type of antenna are used for your handset? So the question is, we are using a millimeter wave communication for our mobile device. So for millimeter wave, we need to okay, Kobita has commented it is 4. So it is clear for you why it is not 4. If it was sub 6 gigahertz, there could be 2 cross 2. So total number of parameters are 4. But here we are talking about the millimeter wave communication. So the channel model is like this. So there is one parameter and there are two parameters. So total parameter is 5. 5 we have to estimate, not 4.
Sir, I think these are taken due to the azimuthal and elevation angle, na? Because
Yes,
when we are calculating manifold vector in that case,
yes.
yeah. So if we have more number of variables, in that case also we have the same number of variables required for the estimation,
But
na?
it will be different from sub 6 gigahertz. It is clear for you, right?
And
Like,
not first, I'm talking about millimeter wave, sir.
ha ha ha. So that will dependent on the dimension there.
Because that is the advantage, na? In the
Yes,
manifold
yes.
vector, we
For
only required.
because it is 2
Yes,
cross 2, right now you don't have advantage, but it becomes 3
yes,
cross
yes,
3.
yes.
At that time you
Yeah,
will
yeah.
get the advantage.
So in that case also we required five variable for the estimation, na?
Ha ha. That sort of thing.
Yes, yes, yes. Thanks.
So the third question I already forgot. That question was for millimeter wave communication beamforming, which type of antenna are used for? So you can think of, we need to perform beamforming there, first of all. That is the main thing in millimeter wave you need to do. So the thing comes here, if we use parabolic antenna or horn antenna, these sort of devices take big space. So for handset, you cannot think of this sort of thing, parabolic antenna or horn antennas. So that is the reason we do like take with equal distance isotropic antennas. This is the D, and then we do the beamforming with particular configuration. Like if we increase the number of antennas, the beams will be sharper. At particular direction, its directivity will get sharper. So that is the reason. Like here, The option will be not be parabolic dish antenna or horn antenna. So it will be array of isotropic antenna. So the correct option will be option C. That is the third C, option C. So let us go to the fourth question. The question is, the beam pattern direction and sharpness for millimeter wave communication is controlled by what? So the first option is transmitting power, second option is only antenna spacing, third option is reflection coefficient of the reflectors, and fourth option is antenna spacing and number of antennas. So let me tell, the first thing here is, if we increase the transmitting power, it does not affect our beam pattern direction on sharpness. Like, it is increasing your intensity. So I am transmitting more power, but that power will depend how the antenna structure has been placed here. It doesn't going to it not going to affect your beam pattern or sharpness. And only antenna spacing. So if we think for antenna spacing, uh, probably we can change the beam direction, but we cannot control over the sharpness at that thing. Like, for isotropic antenna, we just use like equal distance, at and that is already defined. Like, everybody is equidistant with a distance d. So the fourth option is reflection coefficient of the reflectors. So what is reflection coefficient of the reflectors? Like, there could be some reflector in the nature, and we don't have any control over the reflectors here. The reflection coefficient of the reflectors may change your beam pattern or sharpness, but that is unknown to us. Like, if we don't know actually how the reflector going to affect the things, so we are not doing the beam forming type of thing, like changing the direction of the beam pattern and sharpness with the help of reflectors. Like, we do the sort of beam forming from the transmitter antenna side. So the option D is antenna spacing and number of antennas. So antenna spacing, we can already pattern the beams, and with the increase of the number of antennas, what we can do, like, we can increase the sharpness of the beams. So what is the right option here for the question number 4? So the question number 4 will have the right answer, like option D. So this is question 4, and the right option is option D. So the fifth question is the same question, like we repeated few minutes ago. There is a 2 cross 2 MIMO system in a sub 6 GHz channel model, and the number of variables is to be estimated for the channel estimation. So where is the difference for the sub 6 GHz? Like, in millimeter wave communication, we do particular beam forming. Like, the beams does not interfere for in between them. We can think like that. But here, for a sub 6 gigahertz model, there could be the terms. Let me draw this thing. It will be get clear. So there is the first antenna, second antenna, first, second, and this is the receiver antenna here. So if it is not millimeter wave, the beam will go here, and there is the channel path is there. I say it is the first antenna is transmitting and first antenna is receiving. So it is the first antenna transmitting but received by antenna number second. So there will be another path. So it is transmitted by the second antenna and received by first antenna. And this is transmitted by second antenna and received by second antenna. So how many parameters are here? H11, H12, H21, H22. This is not the case for millimeter wave. So for a sub 6 gigahertz, there will be 4 parameters that I have to estimate. But if it was millimeter wave, I would have 5 parameters. That is for millimeter wave. This is the difference between these two. So the correct option will be option A. There are only 4 parameters that I have to estimate for millimeter for a 2 cross 2 MMS system. So option A. This is question number 5. So the next question is array manifold vector in the transmitter side and receiver side depends on what? So at the transmitter side, it depends on angle of departure, the manifold vector, and for the receiver side, it depends on angle of departure. So option A and B says the term only. So the correct option will be option C, both A and B. So for question number 6, option is C, both A and B. So let us solve the question number 7. So question number 7 says the phase associated to the reference point in a array manifold vector containing 5 antenna elements in one antenna array is what? That is the question here. So anybody can answer this question?
0 degree.
Yes. That is the reason. What is the reference point here? So reference point means it is the first, like we are feeding the antenna elements, right? Suppose there are the antenna elements. So the reference point means the first point where the electric signal is going to be fed. So the electric signal comes here and then it gets distributed in this direction. So the phase we can think here is 0 and the phase starts to increase with the distance. Like this electric signal has to cover this small distance d and the phase generates for covering this sort of distance d. This is another d. So for the first thing we can think it is 0 and then it is going to be fed in the nearest neighbors. So the first thing has phase 0 and the phase does start to increase with the number of antenna elements. So the correct option is option A. This is the correct option.
Sir,
Okay, huh? Yes.
sir, I have one doubt. Suppose if the reference is not 000,
Okay.
uh, it is like suppose if it is 00D
Okay.
and one more antenna is presented 00 minus D.
Okay.
So in that case, what will be the phases? And that is 00D is a reference.
Yes. So from my understanding, I can say that the first antenna point,
Mm.
like you have to fed the electric signal, right, to
Yes, yes.
one of them.
Yes.
So it will be in phase with the actual electric signal that has been generated by your system. And then you connect the wire to the next element, right?
Yes.
Like
Yeah.
from D to
Like,
minus D, you have to connect another wire.
yes.
So the electric signal has to cover that path. So
Huh.
that will generate the next phase there. Like for the 2D, distance is 2D, right?
Ah.
So
Yes.
the first point is 0 and then it crosses 2D distance.
Hmm.
So that is the phase that is getting generated. So we can think that 00D is the first point,
Uh,
and then like here you are saying that 000. So this 000 is getting, like, there does not exist any 00 point, right? We always generate our frames.
that's what. Like always, we need to take the distance vector with
Like the
respect to the
first point,
reference.
we are feeding the electric signal, that is
Mm.
the reference point, that should be 000. Like you cannot think like 000 is generated by us, we think what is 00, we fix what is 000. There is no sort of universal 000, right?
Okay.
There is no ending point of x direction. Like we generate our own framework and we define what is 000.
Okay. 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 Like it depends on the user, which he considers as his
Yes,
reference
that
point.
sort of thing. Like how can you set what is 000? Like you can say the fourth element is my first element, and
Ah.
there is minus three element in one side and one element in the right side. So
Yeah.
probably the midpoint is not the reference point here. So but the reference point is at 000. It goes up into up for 3D. Um, if each of the antenna is placed at a d distance, so the last antenna in one of the direction will be at 3D distance, another and here and we at minus d probably. So like C.
Okay.
So suppose we say this is the reference point. So this is D, this is 2D, and total becomes it is 3D in this direction, and it is at minus D. So we set it is 000. Like if we change our own framework, like if we say that this is the first signal that is 000, then
Okay.
this distance becomes 2D and this becomes minus 2D.
Okay.
Okay, thank you.
Okay.
So the correct option is option A, but we have written this. Option A. So the next question is question number 8. The phase associated to every element in array manifold vector in receiver side depends on what? So the first option is position vector of the antenna array elements, and the second option is direction of receiving the signal. Third option is direction of the transmitting signal, and the last option is both A and B. So the question is related to the receiver side array manifold vector. So it has no dependency on the direction of the transmitting side signal, because if there is a reflector, the transmitter signal will be reflected by the reflector, and at what angle it will be reflected nobody knows. So the direction of the receiving signal, it will definitely depend, and position vector of the array elements, it will also depend. So why it will depend on these two factors? Let me write the equation here. So this vector is like sort of e to the power I j phi and dot dot dot. So this is the phase, this j phi, and this phi has the dependency. For the receiver side, I denote it by R, and the lth number, like this is one dot 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 L number of antennas probably are there. So it will be dependent on 2 pi lambda at d cos theta, and it becomes L phi 1 j e to the power L j phi 1. So see, this is the d, and depending on this d, this says that there is a how the position vector works for the antenna elements. And this theta is what? The receiving degree. In like if the array is coming like that and the antenna is here, this is the angle theta r. So it will depend on position vector and direction of receiving the signal. So both the options are correct. So the correct option is option D. Both A and B. This is the correct answer. So the next question is, which of the following corresponds to the unit of field intensity? So if we think for the point field intensity, so this is the probably the solid angle, the direction beam is getting deployed. This is the angle theta. So this is the beam solid angle. So if the antenna is isotropic, this beam solid angle covers the whole globe and this direction, like this is the x, y and z, three direction, the whole direction, and this becomes 4 pi. If it is not isotropic, we can generate the directed beams. Like it becomes like this. So unit of field intensity, it is power by solid angle. So the right option is C. And the last question is the unit of pointing vector. So this is also some sort of equation comes. Question is, last question is, what is the unit of pointing vector? So pointing vector is the quantity that describes the magnitude and direction of the flow of the energy in EM waves. So you can think it also like this. So see, this is the flow of the energy. So what can I think? It is the directional energy flux, and this directional energy flux means what is the power per area meter square, that sort of thing. So the right option will be watt per meter square. So this is the question number, last question for today's session. So all the questions are covered for today. So anybody has any doubt about any question I have discussed today? Okay, I think we can meet then. Yes, next question. Second question. Please clarify second question. Okay. So for the second question, there are two transmitting antennas and two receiving antennas. So for these two, there will be two angle of departure theta t. There are two parameters, and if I think from the receiver side, there are two also angle of arrival for the receiver side. So 2 and 2 is becomes 4, and there is the channel here, and this channel has a gain alpha I according to this equation. So there is only single reflector. So we have to estimate one more point, like here I is equal to 1 to n is equal to 1. So there is only one point here. So alpha 1. So this is another one parameter. So total how much parameter? 4 plus 1 equal to 5. That is the thing here. The option 2B is here. Is it okay? Okay. For sub 6 gigahertz, I already drawn it. Okay, let me draw it. If it is sub 6 gigahertz, we do not use beam forming, right? Like these sort of beams we do not do. What we do, we just have two transmitter antennas and we transmit like this. So this is the first parameter, this is the second parameter, this is the third parameter we have to estimate, and this is the fourth parameter I have to estimate. So for 2 cross 2, it is 4. But if it is like millimeter wave, it is 5. Like they are beamformed, there is no cross term here. That sort of thing you can think of. Okay, fine. Then we'll meet in the next Tuesday. I think there is no doubt for today's session.